This is the Atomic Energy Commission's National Reactor Testing Station. Sagebrush country. Quiet country. 440,000 acres of Idaho's high plateau, home of half a dozen major technical plants where scientists and engineers are studying ways of putting the atom to work for mankind. Here, Argonne National Laboratory has built and tested several types of reactors. The experimental breeder reactor, EBR for short, which demonstrated the possibility of breeding nuclear fuel, was an early tenant of this area. Back in 1951, this reactor was also the scene of a significant piece of history, the first production of useful electricity from nuclear power in the world. The nuclear reactor in operation produced substantial amounts of heat. In a closed system, a liquid metal took the heat to a heat exchanger, where it was transferred to a second closed liquid metal circuit, which carried the heat to a steam boiler. The steam was piped into a turbine to drive a generator. The generator came up to speed, and we had electric power. It was only a token amount, but it was enough to supply all the needs of this particular reactor and its buildings and machinery. EBR was not designed primarily as a power reactor, but among the data it did contribute was more knowledge in the field of heat transfer studies. Many scientists were studying power reactor problems. At Argonne, Dr. Walter Zinn and his colleagues went to work on their concept of simplifying the process by building a new type of reactor in which the water turned directly to steam inside the reactor itself, thus eliminating the heat exchanger. This could be an important advance in power reactor technology. The theory involved in the new design was relatively simple. There would be a sealed pressure vessel containing fuel plates made of uranium alloy. Ordinary water surrounding the plates would act as the coolant and would slow down the neutrons. Neutron-absorbing control rods would regulate the activity level. As soon as the rods were withdrawn, the chain reaction would increase, making the reactor plates hot. Some of the water would turn to steam. Before going further, it was considered necessary to check the safety factors of such a system by an actual test. In experiments with an early version of the reactor in 1953, it was determined that the design would indeed produce steam steadily. It was also proved that the reactor had an inherent safety factor against accidental power rises. Since the moderating water was necessary to keep the nuclear chain reaction going, any excess steam that diluted the water or shoved it out of the core automatically slowed or stopped the reaction. In other words, the reactor had self-regulating characteristics. Tying in this and other experiments, the design theory was now on more solid ground. Work could continue toward electric power production. In this plan, steam from the boiling reactor would go directly to drive a turbine, then through a condenser and back to the reactor in a closed cycle. The turbine would be coupled to a generator to produce electricity. The final step would be a device to get rid of the experimental electricity. A water rheostat, a sort of giant waffle iron, cooled by a water system which would circulate through a cooling tower. A single control center would direct the main functions of all units. Construction of the experimental nuclear power plant, named BORAX, short for Boiling Reactor Experiment, began in early 1955 at the testing station in Idaho, a complex job that can be summarized in a series of brief glances during the course of construction. By late spring of 1955, the reactor tank was completed inside one building, and a short distance away, the turbine was being installed in a separate structure. Then the steam condenser was hoisted and coupled into place below the turbine. We have no complete answer as to how much the future maintenance of the turbo generator will be complicated by radioactivity carried by the steam. Current information suggests that this will not be a major problem in systems of this type. The next item, the generator, was lowered into place beside the turbine. Over in the reactor building, the grid, or framework to hold the fuel elements, is ready for installation. First, however, a set of fuel elements is placed in each of the 4 grid sections in turn to make sure they will fit properly at final assembly. With this check accomplished, the elements are taken out and the empty grid is lowered into place in the reactor vessel, ready for fueling when the time comes. In the meantime, work continues steadily on other parts of the job. The necessary plumbing is installed to all units. From the reactor pressure vessel, steam will go through an overhead insulated pipe to the turbo generator. The return pipe of smaller diameter is just below the steam pipe. A maze of control valves and electronic equipment is installed. All control circuits lead to a trailer located half a mile away, since the plant, the first of its kind, is to be given severe safety tests. The control trailer is near the older experimental breeder reactor that gave us our first useful electricity from the atom. In addition to controls, many kinds of meters and recorders are located in the trailer. Back in the power plant area, the roof and walls of the turbo generator building are completed. At the end of this structure, the water rheostat, the waffle iron to get rid of surplus electricity, is assembled. Pipes and the pump to circulate the water it will heat are connected up to flow the water over the louvers of the cooling tower. The non-nuclear part of the project is finally finished. Inside the reactor building, the last of the 5 control rods is inserted in the grid as a basic safety measure before loading the fuel elements. Next, the fuel elements of uranium alloy are loaded into the grid. With the fueling completed, the pressure cap is placed on top of the vessel and bolted down. The top cover slab is pulled in place over the vessel. With the top cover slab in position, the control rod extensions are passed through the cover slab and pressure cap, connected to the control rods, and packed to prevent leakage of steam. The machinery to operate the control rods is moved into position and connected to the rods above the slab. With this, the reactor is essentially complete. After a series of checks of instrument and servo controls, all operational circuits to the distant control trailer are active, and the reactor can now go critical. A number of careful tests are made with the reactor at low power to learn its operating characteristics. Then the time comes for a test at full power. The reactor vessel has been charged with preheated water, and the control rods are withdrawn from the reactor core. Very soon, the first signs of activity are registered as the counter panel shows an increasing number of neutrons. The critical point is reached and passed, and indicators show the rapid rise of the water temperature in the reactor core. Steam pressure comes up to 300 pounds per square inch at a temperature of 418 degrees Fahrenheit. This is the set operational level, and the control valve is opened to feed steam to the turbo generator, which picks up speed. At this point, instrument readings take over the story. The instruments say the output lines from the generator are hot. The new type boiling reactor is, for the first time, producing a steady 14,000 kilowatts of heat and about 2,000 kilowatts of electric power. power enough to supply a small city. The next obvious thought was, well, why not supply a small city just to complete the experiment? There was one about the right size only 20 miles away. Arco, Idaho, a normal western community in a range and farm area with a normal quota of schools, churches, stores, homes, and humans. Nearly 1,200 humans. Here was the chance to make one more small slice of history. Arco, Idaho could be the first American town to be lighted experimentally and exclusively by nuclear power, power from this new kind of reactor. It was found the transmission of the electricity would not be difficult. The existing network could be easily adapted. Somewhat simplified, the normal circuits of importance to the project were a feeder line of the Utah Power and Light Company into Arco, and a branch of this line to serve the National Reactor Testing Station, including Argonne's BORAX facility. From the testing station, an old unused line connected with the Arco substation. It was necessary to build a circuit so that BORAX could supply its own power requirements, and a transformer was needed to step up the BORAX line voltage for distance transmission. The project needed a switching arrangement at the testing station to cut BORAX off from conventional power and then send BORAX nuclear power up to the Arco substation. At the substation, another switch would isolate Arco from Utah power and then feed BORAX power into the town. All preparations were completed by mid-July. A few days later, shortly after sunset, BORAX was standing by with full power, ready and waiting. Transmission lines were ready. Arco was ready. It was after dinner time, and people were going about their evening's business. Several hours later, the BORAX reactor is phased in on schedule to supply its own electricity. Then, BORAX is disconnected from conventional power, and its nuclear power is sent on toward Arco substation. In town, the lights are still bright. Then, the substation cuts off conventional power and feeds in BORAX nuclear power. Arco sees new light, light from nuclear power. Here in Arco on July 17, 1955, this new type of power reactor supplied citywide the kind of energy which will someday power man's factories, warm his home, cook his meals, and in many other ways make his life richer and fuller in a peaceful world.